For centuries, a whisper echoed through shadowed laboratories. It was the dream of alchemy, turning humble lead into glittering gold. This wasn't just about wealth, it was about understanding the very essence of matter. A quest that captivated minds, from ancient Egypt to medieval Europe. They sought the philosopher's stone, a mythical substance, said to grant eternal life, and of course transmute base metals. Lead, heavy and dull, was their prime candidate. Gold, radiant and incorruptible, their ultimate prize. This pursuit laid groundwork for modern chemistry. It fueled curiosity. The alchemists, in their own way, were pioneers. They experimented, they observed, they meticulously recorded their findings, however cryptic. The universe, it turns out, is a grand alchemist itself. The cosmos whispered, yes. The alchemists toiled with fire and crucible. They spoke of sulfur and mercury. Mystical principles they believed governed all transformations, but the universe operates on a different set of rules. Rules written in the language of atoms. Tiny, fundamental building blocks of everything. To truly understand transmutation, we first had to understand these particles. The journey took us from smoky labs to the gleaming halls of scientific discovery. A new era of understanding dawned. It began with the realization that elements were distinct, defined not by mystical essences, but by their atomic nature. John Dalton, in the early 19th century, revived the atomic theory. He proposed that each element consists of unique atoms, atoms that could combine to form compounds. But the atoms themselves were thought to be indivisible, immutable, unchangeable. Lead was lead, gold was gold, and never the twain shall meet, or so it seemed. The electron was found, then the nucleus. The atom, it turned out, had an internal structure, a dense core, the nucleus containing protons and neutrons, surrounded by a cloud of nimble electrons. This wasn't the indivisible sphere Dalton envisioned. This was a miniature solar system, dynamic, complex, and crucially, potentially changeable. So, what truly distinguishes lead from gold, or from any other element on the periodic table? It's not its color, its weight, or its shine, fundamentally. These are just outward manifestations. The real difference lies deep within, inside the atom's core, the nucleus. Here, tiny particles called protons reside. The number of protons defines an element, it's the atomic number. The element's unique, unchangeable ID card. Or is it? Lead, our humble starting point, has 82 protons, 82 positive charges packed into its nucleus. This number dictates its chemical behavior. It determines how lead atoms interact with other atoms. It makes lead, well, lead. Heavy, soft, a dull gray. Useful for many things, from batteries to radiation shielding, but decidedly not gold. Gold, on the other hand, is the aristocrat of elements. It has 79 protons in its nucleus, just 3 fewer than lead. This seemingly small difference changes everything. Gold is rare, beautiful, and incredibly unreactive. Its atomic structure makes it precious. So, the challenge becomes clear. To turn lead into gold, you need to change the number of protons. A delicate, yet immensely powerful operation. The dream of alchemy never truly died, it simply evolved, it shed its mystical cloak, and donned the precise language of nuclear science. We call it nuclear transmutation, the process of changing one element into another, or one isotope of an element into another. This isn't about potions or incantations, it's about manipulating the very heart of atoms, the nucleus where protons and neutrons reside. The key insight came in the early 20th century. Scientists like Ernest Rutherford showed it was possible. They bombarded nitrogen atoms with alpha particles and detected hydrogen. Nitrogen had been changed into oxygen in the process. This was the first artificial nuclear transmutation, a monumental achievement. The alchemist's dream, realized through the power of science. Not with lead and gold initially, but the principle was established. Elements were not immutable. Particle accelerators are the modern alchemist's crucibles. These immense machines use powerful electromagnetic fields to accelerate charged particles to near the speed of light, giving them enormous kinetic energy. This is the toolkit for turning lead, theoretically, into gold. Section 5. Cocorico. France achieves the unthinkable. In 2025, a headline flashes across the globe. France, the land of Pasteur, Curie, and Becquerel. Scientists at the Orléans Transmutation Laboratory have converted lead into gold. The news sends ripples through the scientific community and captures the public imagination. The age-old quest has reached a new milestone, a testament to human ingenuity and persistence. Reports speak of years of dedicated research, meticulous calculations and countless experiments, pushing the boundaries of particle accelerator technology, and refining nuclear interactions. The quantity of gold is minuscule, far too little to disrupt the gold market. But the symbolic value? Immense. Section 6. How they did it, a symphony of subatomic particles. So what was the secret behind this French triumph? How did they coax lead, atomic number 82, to shed 3 precious protons and become gold, atomic number 79? The process, as you might imagine, is incredibly complex. It involves harnessing immense energies and directing subatomic particles with pinpoint accuracy. Think of it as performing surgery on a target billions of times smaller than the eye can see, using tools forged from the very laws of physics. It's a delicate dance of force and matter. The heart of their experiment lies in a new generation particle accelerator, located deep beneath the French countryside, perhaps near Orléans. This marvel of engineering, let's call it Le Grand Accélérateur National, LGAN, is designed for unprecedented precision. It takes a specific isotope of lead, likely lead-208, which is relatively stable and abundant. This lead forms the target. Then, the accelerator fires a carefully tuned beam of particles at it. Not just any particles, and not just any energy. The choice is crucial for the desired outcome. The French team employed a beam of highly energetic protons or light nuclei. Section 7. More than just gold. The true treasure of transmutation. While turning lead into gold captures headlines, the real value of this French breakthrough isn't about creating wealth. You won't be mining gold from particle accelerators anytime soon. The cost of producing even a single gram this way would vastly exceed the market price of gold. The true treasure lies in the deeper understanding and control of matter. It's about the scientific and technological advancements and the potential applications that go far beyond shiny metals. This is where the discovery truly shines. Its implications stretch into medicine, energy, and fundamental research. Consider medicine, for instance. Nuclear transmutation is already vital for producing medical isotopes. These are radioactive forms of elements used in diagnostic imaging, like PET scans, and in cancer therapy, targeting and destroying tumor cells. The ability to more precisely create specific isotopes, perhaps even new ones with unique properties, could revolutionize medical treatments. Imagine custom-designed isotopes for personalized medicine, targeting diseases with unprecedented accuracy. This French advancement could refine these production methods. In the realm of energy, the implications are more subtle but still significant. Section 8. The Golden Catch Limitations and Practical Realities. Now, before we all rush to build particle accelerators in our backyards, it's time for a reality check. A dose of cosmic perspective. The French achievement is a monumental scientific feat, but turning lead into gold on an industrial scale? That remains firmly in the realm of science fiction for now. The limitations are significant. The practicalities are daunting. The universe doesn't give up its secrets or its treasures easily. There's always a catch, especially with gold. The first and most obvious limitation is energy. Altering the nucleus of an atom requires tremendous amounts of it. Particle accelerators are among the most energy-intensive machines ever built. The energy needed to produce even a few atoms of gold far exceeds the energy you'd get from, say, burning that gold as fuel, if you could. The process is incredibly inefficient in terms of energy balance. You put in vastly more energy than the value of the gold produced. It's like using a sledgehammer to crack a nut, and the nut is microscopic, and the sledgehammer costs billions. Then there's the yield. The amount of gold produced is infinitesimally small. You might bombard tons of lead for years and end up with less gold than you'd find in a discarded smartphone. Section 9. A glimmer of gold, the future forged in accelerators. So what does this French breakthrough signify for humanity? It signifies progress, our relentless curiosity, our drive to understand and shape the world. Each discovery expands our knowledge and refines our tools. It opens up possibilities we can't yet imagine, discoveries that seem esoteric at first but later become foundational. These once abstract concepts now underpin our modern world. The ability to manipulate atomic nuclei could follow a similar trajectory. The future possibilities are tantalizing. This achievement encourages us to ask, what if? And then, to find out. The true triumph is the knowledge gained,